So in the previous slide, you have learned about the inward ROC, outward ROC, and ring shape ROC. So let's see what are the effect of equation towards the ROC types. So first of all, that we are going to look at the outside the outward ROC. So outward ROC, if you see here, this is the corresponding equation given here. So you have the equation which is given by xn equivalent to a n u n. So imagine that if you have this type of signal, means that it's going to be plotted as the right-sided sequence. Means what does it mean by right-sided sequence? Is that you have the signal which is starting from 0 and you have the signal towards the positive infinity. Okay, so this is called the right-sided sequence. So when you have a right-sided sequence, automatically you will know that the ROC that you get is the outward ROC, which is Z is more than R. The second one is that we have the inward ROC, which is when you have Z less than R. So this one, if you see the corresponding signal, is that is given by xn, okay, equivalent to minus a to the power of n, u minus n minus 1. So don't be too scared about this signal. It's just the representation of the signal when you have a sequence which is left-sided sequence. Okay, so left-sided sequence means that when you have the signal is 0, and then from minus 1 you will have the signal towards the minus infinity. So this is what it means by left-sided sequence. Left-sided sequence, automatically you know that the signal will have Z less than a value or R value. If you have the right-sided sequence, is that you have Z is more than A. Okay, and the third signal is that when you have the region of convergence in a donut shape type like this. Okay, so donut shape type like this is that when you have the combination of the left-sided sequence and the right-sided sequence, meaning that you have the combination of the right-sided plus the left-sided equation over here. So it means that you have both signal in the positive side and another in the negative side. So when you have both-sided sequence like this, it means that you will expect that you will have the region of convergence in the form of a ring-shaped type ROC, which means that you have Z is less than R2 for this case, and Z is more than R1. Okay, so three main types of region of convergence. So outward type, inward type, and also the ring-shaped type. So let's go and see to the pole zero analysis. If you remember in the Laplace transform, you can actually rewrite this equation as xs, okay, equivalent to ps over qs, which is in the Laplace form, in the s-plane form. So when you have this equation, is that you have the upper part is we call as the numerator and the lower part is the denominator. Okay, so what it means that you have the upper part is the zeros of exact, and you have the lower part denominator is for the pole. So this is where actually when you plot, you find what the stability of the system or signal using the Laplace transform. You can actually plot it in the root locus manner, so using the zero and poles here. Okay, similar to that, Z transform can be actually use the same representation similar to what you have done in the Laplace transform. So for the case of Z transform is that, okay, you may see that the Z transform can be in terms of one-sided, which is unilateral. So I have explained just now that you have the right-sided sequence and the left-sided sequence. So this right-sided sequence and left-sided sequence is actually named as the unilateral, means that one-sided only. And the second one is that you have the two-sided sequence, means that you have the both positive and negative side. So this is what we call as the bilateral signal. Okay, so let's go and see how does the equation look like for the unilateral signal. So unilateral signal is that when you have x(z) equivalent to summation of 0 to infinity x n z minus n. So if you see here, this is for the right-sided sequence. Why? Because you have from 0 to positive infinity. You have 0 here to positive infinity. So if you were to write using this equation for the left-sided sequence, is that you just change it. So you have from minus infinity to 0. So you get the left-sided sequence over here. Okay. So for bilateral signal is that you have both sides. So you have the positive infinity and minus infinity. So it means that you have from summation of minus infinity to infinity x and z minus n. So if you see here, this does not change. What changes is only the summation point here. Okay, summation is depend on the signal sided. Okay, so this is what is the explanation for unilateral and bilateral. So generally, Z transform is represented as a ratio of two polynomials. So we have learned that you have the numerator and denominator just now. So you can actually write xz equal to b0 plus b1z inverse 1 plus b2 and so on over 1 plus a1z and so on. Okay, so we call this as the polynomial. This is the in a form of polynomial form. Okay, so let's go by looking at these two equation here. Okay, let's do an example. Okay, so example 1 is determine the Z transform of the signal xn equal to un. So means that your signal xn is given by un. Un is what? If you remember in chapter 1, you have learned that un is a step input. So step input for continuous signal is like that, like this, right? Okay, but if you look in the Z transform, is that it's a representative of a discrete time signal. So it means that you are not going to use this signal, but instead you are going to use it in terms of discrete time like this. So it will start from 0, 1, 2 until infinity. Okay, so reason why your xn here will be represented as this signal. Okay, so example, maybe in your final exam, this signal xn, the graph won't be given. You are only given this statement. Okay, this statement only. Okay, so xn equal to un. So find the ROC. So what you need to do is that you need to draw out, understand what type of signal it is. Is it a positive? Is it a right-sided sequence? Is it a left-sided sequence? Or is it a combination of both right-sided and left-sided? Okay, so if you see here, that is actually a right-sided sequence. Okay, so we start with getting the solution first. So determine the Z transform. So what you need to do is that get the exact for this xn signal. So exact is, by according to the formula, is that you have exact equal to summation of xn z minus n. So for this case is that we are going to use the polynomial term just now. So you have x. If you remember, you can actually write up this equation based on the signal or integer given here. So you have n value, so n at 0. So n0 x0, here you have a value, plus x1, so you have x0, z minus 1, so basically z minus 1 is, you get 0, so equal to 1, plus, because this is summation, so you have x, substitute n value inside here. Okay, so you have x1 z minus n equal to 1 lah. So z inverse z minus 1, so over z, plus z2 z minus 2, so means that z2 bracket 2 over z squared, plus and so on. So you get this equation. Okay, so we continue in this form. So you're going to write out x equivalent to un z minus 1. So this equation, you can rewrite it and it will become this equation. So x0, what is the value for x0? X0 is 1, so that's why you have 1 here. Okay, 1 here. Okay, 1 plus x1 is also 1, so you have 1 over z, so this is 1 over z, plus x2 is 1 also, 1 over z squared, so you have z minus squared, plus and so on. Okay, so after you rewrite this, you can actually rewrite the equation into this form. So you will get 1 over 1 minus z minus 1. Okay, so if you rewrite this, okay, you put it in either in this form or this form, anything is okay, either form is okay. So you can get z over z minus 1 or 1 over 1 minus z minus 1. So how to determine the ROC? If you look at the question just now, find the ROC. Okay, so find the ROC is that you're going to look at this form, means that you have 1 over 1 minus, for example, if you see here is that z minus 1. So look at this value here, only take this value, z minus 1. Ignore the minus here. Okay, z minus 1 here. Take this value. Okay, z minus 1 is actually 1 over z. So less than 1. So start with this. This is the format. Okay, so 1 over z is less than 1. So z is more than 1. So you can actually draw out this into this region of convergence. So you have 1 here. You have the unit circle. So z is more than 1. So you have this region. Okay, z more than 1, you will get this equation. So by referring to the z transform table, if you look at the table, is that it was given that if you have un, you have this equation and the region of convergence is z more than 1. So actually you are proving that for the step input signal is given by this z transform equation, and the region of convergence is z more than 1. Okay, this is what it means. So as a summary, you can actually see that just now what you did was you are using the right-sided sequence, but you do not have a n value, right? So this one do not have any value, so you only have un. Okay, so un it's still a right-sided sequence, so you have it more than one value. Okay, so let's go to the second example, is where you have a signal where you have a and un. Okay, means that maybe the signal is not a step signal like this, but you have a value decreasing, okay, like this. Okay, means that it's decreasing like this, a and un. So here is that determine the z transform and sketch the region of convergence. Okay, by default, if you're given this equation, the first thing that you can directly do is that by referring table directly. Okay, because it's just by looking at it, matching it to the table. So if you look at table, you can find out in the table there is a value a and un. Okay, so the equation given for the z transform is that z over z minus a, where it's given for the region of convergence is z is more than a. Okay, so directly you get the answer, determine the z transform, which is this one, answering for question A, and sketch the region of convergence is B. But here this is an example, so let's go and see how you actually prove it. Okay, so to start off this equation, find the z transform for x and value here. So use the general equation exact equal to summation of x and z minus n. So just substitute the value x and here into this equation, then you get this value. Okay, then arrange it, you get this, and finally you get in this equation. Okay, so take out this value a z minus 1, so you have a over z less than 1, z is more than a, meaning that, okay, you will see that actually if you draw out the region of convergence, for example, you have this unit circle, okay, and a is actually maybe somewhere here, a, okay, region of convergence, this is a, so a is here, so it means that you have the region of convergence actually covering the unit circle. Okay, means that the answer is that for this it's stable. Okay, so okay, this one is how to sketch it. So sketch it is that by getting it the region of convergence. So after you sketch it, then you see that the a value is actually covering the unit circle 1 value. Okay, so next we go to the third example, which is we are going to look at the left-sided sequence. Okay, so you are given this equation. Okay, if you remember this, we were talking about the left-sided sequence. Okay, left-sided sequence is given by minus a n u minus n minus 1, so which is this equation. So it's a left-sided sequence. So left-sided sequence is that from minus 1 until minus infinity. Okay, so determine the z transform and sketch the region of convergence. So like the previous example is that you can directly refer to the z transform table. So referring to that directly, you will get the z transform will be z over z minus 1. So you see that this equation is almost similar with the example 2 just now, z minus a, right? But the difference is that the region of convergence, for example 2, the region of convergence is z more than a. However, for the example 3 is that the region of convergence, it is z less than a. So for the left-sided sequence, the region of convergence is actually less than a, but having the same equation. Okay, so let's look at the example, how you can actually use the general equation to actually prove it. So xn equivalent to minus a n u n, so just substitute this value xn into here, then you will get this equation. So referring to this, you can actually rewrite again, just ignore whatever minus n minus 1 here. Look at this graph here. Okay, you will see that you start with the value, you have the value of minus 1 until minus infinity, right? So you see that you have the minus part here, so you start with minus infinity to 1 a n z minus n. Okay, and if you see here is that you can either write it like this or like this. Okay, example here I give here on the right side here, look at this. So you have summation of n equal to minus 3 until minus 1. It means that on the left-sided sequence, a n. So you have a to the power of minus 4 plus a minus 3, which is the same with this equation, which is given by summation of n equal to 3 to 1 with a minus n. So the difference is that you have a here, this is minus n, this is n only, and then you have here the positive side 3 to 1, and then this is minus 3 to minus 1. So you will still get the same answer, a minus 4 plus a minus 3 until a minus 1. Okay, so these two is same. Okay, and equivalent to, why you have 1 here is, if you see here at the x equal to 0, there's no value, so that's why you have 1, okay, minus summation of a minus 1 z minus 1, which is this value. Okay, so you will get this equation. Okay, you can actually rearrange it. It will become this equation, and you have z over z minus a. And for this case is that after you rearrange it, okay, you take this value, okay, you will get that z is less than a. So for the B part is that to sketch the region of convergence. So you already get that z is less than a. So you just draw out the unit circle, which is 1. This is, you need to always draw out the unit circle. And where is the location of a? So z less than a is here. So if you see here, the region of convergence, the signal for the signal is not stable because it's not including the unit circle. Okay.